Hello everyone, my name is Farjana Samia. Today I am going to present one paper. Name is GreenKGC, a lightweight knowledge graph completion method. This paper published by Wang et al. In the year 2023 at ACL. I am presenting this presentation in course Advanced Topics and High Performance Computing. The course instructor is Dr. Ali Jannesari. So this is the outline what I'm going to cover today's presentation. First of all, the problem statement, motivation, related work. Then I will cover the proposed method, GreenKGC framework. Then I will discuss about the methodology details, experimental setup, experimental result evaluation study, discussion and limitation, conclusion and future directions. So let's now start with the problem statement. So knowledge graph are fundamentally incomplete. So knowledge graph completion suffers from missing entities and incomplete relations. Real world cages like freeways have massive amount of missing data. For example, FB15K237 filtered from freeways has only fraction of true relations. So this missing or incompleteness has serious consequences. When triples are missing, it degrades the performance of downstream AI application. For example, question answering accuracy, recommendation system quality, information extraction completeness. So this slide covered the motivation. The prior KGE methods rely on high dimensional embeddings, for example 200 to 500 dimensions, which is quite heavy models and slow inference. Neural classification based KGC method achieve good performance but are computationally expensive. So we can see that there is a clear need for a lightweight, efficient, fully Euclidean KGC framework that perform well in low dimensions. So as you can see, high dimension KG embeddings, which is quite heavy model and gives low inference, and low dimensional KG embeddings, which is lightweight model and give the fast reasoning. This is the main goal of this research work. So now moving on to the related work, the knowledge graph completion. The existing approaches can be broadly organized into three categories. The first is embedding based KGC, which is embedding based KGC. And actually, what is embedding based KGC? Like, this approach learn vector representation for entities and relations, then use geometric operations like translation or rotation to predict the missing links. And second is classification based KGC. Instead of relying purely on geometric operation, these methods treat link prediction as a classification problem, often use neural networks to score whether a triple is valid or not. So the low dimensional KGE is basically especially focusing on learning compact embedding, often in nonlinear Euclidean space like hyperbolic geometry, to reduce the model size while maintaining the performance. So let's go through each category. In embedding based methods, trans-E models relations as translations between entity vectors. Rotate E basically extends this idea by using rotation in complex space, and which helps capture symmetric and asymmetric patterns. There are also a scaling and reflection based model, which is basically specialized on transformations for logical patterns. However, all these require high dimensional embeddings and making them slow and memory intensive. In the classification based KGC, there are NTN, which is neural tensor network with textual features, conv-KV, which is 1/3 convolutional with fully connected layer to score the triples, conv-E, which reshapes the embedding into 2D images, and for convolution, and KG-boost, to use one classifier per relation is not scalable. So the limitation here is the neural models have long inference time and large parameter counts. In low dimensional KGE method like MARP and ATTH use hyperbolic space to efficiently capture hierarchical structures. MARD and DE and dual DE basically use distillation to compress high dimensional models, but the challenge is that hyperbolic vectors don't integrate well with standard Euclidean downstream tasks. So there is a clear research gap. There is need lightweight KGC in Euclidean space, fast training, competitive performance. So the researchers of this research work proposed one method named GreenKGC. This GreenKGC framework consists of three major modules. First of all, the representation learning. Second is feature pruning and decision learning. Representation learning is basically use existing KGE, for example trans E and rotate E, for 500 dimension embedding, and feature pruning is basically use the like discriminant feature test DFT selects the discriminant dimension, which reduced almost 80 to 32 dimension from 500 dimension. And in the last module, which is decision learning, here they have used the lightweight classifier, particular particularly decision learning, instead of using simple classification scoring function, they employ binary classifiers, especially gradient boosting machine, to predict whether a triple is valid. These classifiers operate on the pruned low dimensional features and learn complex nonlinear decision boundaries. So the key advantage of these modules are fully Euclidean pipeline, unlike hyperbolic KGE methods, enabling seamless integration with downstream ML tasks, does not require retraining new low dimensional embeddings, fast, scalable, and modular. So this is the main architecture of GreenKGC framework. So as you can see, there is a three part which represent the three major module. A is a representation learning, B is a feature pruning, and C is a decision learning module. Here, and what actually GreenKGC wants, it wants to do the KGC efficiently. So instead of using embedding like 500 dimension, it tries to keep only the most useful dimension like 32 dimension, while still predicting missing triples correctly. So in the representation learning, they took the knowledge graph and they use the standard model like trans E and rotate E, and they create the high dimensional entity relation representation. Here their output is 500 dimensional entity or relation embeddings. After they have done the feature pruning step, here they, as you can see, there are many KG partitions, subgraph, which is subgraph. GreenKGC splits the KG into smaller parts. Why they have done so? Because to make the pruning and learning easier and scalable, instead of analyzing all the relations together, it handles chunks of KG. And now they have 500 dimension and ask which embedding dimension actually helps separate positive versus negative triples. GreenKGC uses discriminant feature test, DFT. Each dimension is scored by how well it distinguishes positive triples, true facts, or negative triples, corrupted or fake triples. And then it removes the dimension that are noisy, redundant, and not helpful for classification. So it reduces dimension from 500 to 32 dimensions. So after they create low dimensional feature triples, here after pruning for each triples, now they have small feature vectors which is 32 dimensions. What is check marks and the cross marks in the figure? It mentions like some are dimensions helpful and some dimensions are noisy and removed. So here they have their output is from these part B, their output is 32 dimension discriminative triple feature vectors. Lastly, they have the they have the decision learning, where they have used the binary classifier for each partition, as you can see. So why they have done so? Because multiple classifier partition can have different classifiers, and they give 32 dimension triple feature vectors as an input, and here 0 means they are likely false triple, and true and 1 is likely true triples. So here they got the probability score soft levels for each triples. So this is the main architecture of GreenKGC framework. So I'm deep dive onto the each module. Each module, the module 1 is representation learning. It uses standard embedding models, trans E and rotate E. It generates high dimensional expressive embedding, require no architectural modification, making it fully compatible with existing KGE pipelines. These embeddings become the input to feature pruning. So the second module is feature pruning. They have used a discriminant feature test, DFT, to evaluate each embedding dimension for class separation ability, which means DFT looks at each embedding dimension independently and asks, does this dimension help distinguish correct triples to incorrect ones? And then they remove the redundant or non-discriminative features. So dimensions that do not contribute to classifications are considered noise and are pruned away. After pruning, they produce low dimensional discriminant feature KG features, DFT vectors, and multivariate extension handles multiple dependent variables jointly. They benefited reduces dimension without losing KGC reasoning power. So The DFT score formula is this, as you can see, the between class variance by the within class variance. What does the between class variance means? That how far apart positive and negative triples are along dimension D, and the and this means how spread out the values are within positive or within negative. So overall, this means the positive and negative triples are well separated. Values with each class are compacted. So if a dimensions has high between class variance and low within class variance, it clearly separates positive and negative triples, so it is a good features. So dimension with low DFT scores are removed. So this quantifies how effectively a given dimension separates positive versus negative triples, making it ideal for identifying useful embedding features. So the last one is decision learning, this module. So here they have applied lightweight classifiers with negative sampling to predict triple validity, operates on DFT prone low dimensional discriminant vectors, reducing computation significantly, learns effective decision boundaries with far fewer parameters than neural KGC modules. So why they have used classifier instead of simple scoring function? The traditional KG models, for example trans-E, use distance based scoring resulting in linear decision boundaries. Real world knowledge graph exhibit complex. This is the main reason they have used the classifier. So the nonlinear relation pattern. So the classifier they have used, the gradient boosting machine, can learn nonlinear decision boundaries, model feature interaction, capture a relation specific pattern. So the dataset they have used are GreenKGC is evaluate on 4 widely used KGC benchmark dataset. So so as you can see, like first of all they have used the FB15K237 dataset, which has the 14,541 entities and 237 relation, which is derived from Freebase and contains real world factual knowledge. And the WN18RR has like 40,943 entities and 11 relation, and this comes from WordNet and represent a lexical knowledge graph with hierarchical structure. And Yago 310 is about 123,143 entities and 32 relation. It is focusing on person attributes and biographical facts. And finally OGBL Wiki KG2, which is massive, 2.5 million entities and 535 relations from Wikidata. This is their large scale test for to prove GreenKGC scales. This dataset varies significantly in scales and structure complexity. For FB15K and Yago 3 are instance based KGs, while AW18RR is concept based with abstract hierarchies. So this diversity lets them comprehensively evaluate where GreenKGC excels and where it faces challenges. So now the experimental setup, the dataset what I told, they have used the matrix, they have used the MRR, which is mean reciprocal rank and hit at k, and parameter count inference time. Hardware they have used the baseline KGE training NVIDIA Tesla P100 GPUs, and classifiers training inference AMD EPYC 7542 CPUs. So there is the experimental result they have done. They have done in this table. This is showed the result of link prediction in low dimension, which is 32 dimension, and they outperformed in AB15K and Yago 310, these two dataset, but face challenges on WN18RR because what I have mentioned, like these two dataset AB15K 237 and Yago 310 are instance based KG, and WN18RR is concept based KGs, but it has hierarchical structure. So it is the reason they have told in their paper that this structure is hierarchies, so they have faced challenges in these dataset. So they outperform in these experiment, they outperform these two dataset. So here is the main observation. I can see here, like their strong performance on instant kgs, which is AB15K and Yago 3. AB15K have like 6.5% improvement on MRR, and Yago 310 has even more, 14.1% MRR. So how they have got, the first they use the nonlinear classifier, allows GreenKGC to model complex relational pattern that simple distance based scoring cannot capture. Second, DFT performs supervised feature selection, which preserve discriminative dimension better than unsupervised methods like PCA. Finally, exceptionally hard negative sampling forces the model to learn fine-grained distinction. So now going on to the W118RR, which is concept-based knowledge graph with strong hierarchies. This improvement is lower. This is expected because Euclidean embeddings are less suitable for hierarchical reasoning, and GreenKGC inherits this limitation from base embedding. So the key insight from here, like GreenKGC excels when baseline embeddings are strong. Powerful decoder classifier compensates for low dimensions. So there is another experiments here they have done, showed that parameter efficiency. So they here their smaller showed that smaller model actually outperform larger ones. So in this table they have evaluated how reducing embedding dimension affects performance. GreenKGC compress 500 dimension to 100 dimension and still improves and matches accuracy while using the 1/5 of the parameter. Here basically they wanted to show that they reduce the dimensions and they have reduced the parameter as well, to reduce the computations null cost. So they most of the time they outperformed or improved in their results. So this shows that the smaller model actually outperformed than larger ones. So their key observation here from this experiment is low dimensional GreenKGC models, which is 100 dimension outperform or match the 500 dimension baseline for both trans E and rotate E across all dataset, and parameter reduction is dramatic. So there is another experiment they have done with their large or huge dataset, which is OBGL wiki KG2 dataset, and they showed that this GreenKGC outperform in these dataset as well, and this proved that their scalability of their framework, and even GreenKGC performs well when they have aggressively reduced the embedding dimension on a very large knowledge graph. Despite using far fewer parameters, GreenKGC maintains strong performance, demonstrating good scalability actually. So here is some observation of that experiment. Even with 80% of parameter reduction, GreenKGC achieved competitive or improved MRR, and result on OGBL and wiki KG2, which is 2.5 entities, show that GreenKGC scales well to very large kgs as well. Scalability, as I have told, that OGBL wiki KG2 is extremely large, which is 2.5 million entities, yet GreenKGC remains stable and effective, indicating excellent scalability of the pruning and decision module. So the ablation study they have done, and they have showed that their component, when they have used all their component, they got outperformed in AB15K and W118RR. Like here they have mentioned, like without DFT performance drops, which confirms discriminant pruning importance, and without decision learning classification boundaries weaken, and different pruning ratio identifies optimal decision dimension reduction, different embedding backbones, which is trans E and rotate E. So this is the main table of feature pruning. So there is a slide which has the discussion and limitation. So first of all, the dependence on initial embeddings. GreenKGC is a performance relies on the quality of the base KGE models, and poor embedding limit pruning effectiveness, and assumption of discriminative dimension. DFT assumes that useful class separable and feature exist. Performance may degrade on extremely noisy or sparsely connected cages. Lightweight decision module, while efficient, the classifier may underperform on very large or highly complex cages where deeper neural models capture richer relational structure. Computational cost of multivariate DFT. Multivariate DFT can become expensive for a very high dimensional embeddings, although still cheaper than retaining deep KGE models. Overall, these limitations highlight the trade-off between efficiency and expressive power in KGC models, emphasizing the need for adaptive pruning strategies that respond to the dataset structure and noise. So the conclusion and feature direction is GreenKGC introduces a compact, efficient, and modular KGC framework that operates fully in Euclidean space. Discriminant feature test (DFT) is the key more innovation, enabling effective low-dimensional representation without retraining embeddings. The method achieves strong accuracy while significantly reducing computation and memory cost, and outperforming high-dimensional and hyperbolic models. Feature direction can be include adaptive pruning strategies, integrating deeper classifiers for complex cages, and applying GreenKGC to large-scale real-world knowledge base. So that's all. Thank you for listening.